All right, so in 1970, the US population was 203.3 million. That's probably going to be our initial value, our A value. By 2007, it had grown to 300.9 million. So there's probably going to be another, like a point on the graph. So if I think about what that would look like. If I don't want to write 2007 there, I want to use the change in the time. So going back to what they told us about that. So 1970 to 2007, that's 37 years. So then our A amount, A value, is 203.3. We'll write a model and equation of the US population P as a function of T. Is the growth rate. So P of T equals A times 1 plus R. This is a growth problem. So we need to know A in order to be done with this, and we need to know R in order to do this. So we definitely have A, and we have this other value, so which should be our, like our T, and then this P of T. So you can see that once we plug all that in, the only thing we won't know would be R. So we're going to go ahead and solve for R again. So 300.9 equals 203.3 1 plus R, all to the 37th power. So I want to solve for R. I want to get rid of division multiplication first. So divide by 203.3. So let's see what that is. I forgot the numbers. Let's see. 300.9. So I really don't have a good idea of what rounding to do here. Let's go to the nearest hundredths there, since the next one's way down there. So it's 1.48. So now I need to get rid of that 37th power. I'm going to do that with a 37th root. Definitely something we're not used to, but I'm going to talk to you guys about in class. Instead of that, we're going to do 1.48 to the it's crazy loud. 1/37th power, so 1.48 to the 1/37th power. So make sure you put parentheses around your exponent there, else that will not work. So you get 1.01. I'll show you just the difference here with that rounding, see how big a difference that makes. So yeah, really not too much difference. So I'm gonna go ahead and round to the thousandth here. So it'll be 1.011. Again, I don't really give us any direction here on what to use, but subtracting 1, I mean R would be 0.011, so that'd be 1.1%. But we don't really need that. What we are trying to do is write that function. So now we know A, we know R, so we can go and write the function. So P of T equals A, which was 203.3 times 1 plus 0.011, all to the T power. So again, we're using that A value, which we knew, didn't mean to write that. A value, which we knew from the beginning, and that R value, which we just found there. All right. We are not going to do this since you guys don't all have access to graphing calculators. Last thing here is looking at compound interest for like money, so how you earn money in a bank account. So we have a formula here. It's a slightly different formula because compound interest means that the interest will earn interest. And so you start off with A, which is going to be your final amount in the account. So watch out for that switch here. And then P, which is going to be the principal, which is the initial amount, the amount that you put into the account. R, of course, is the rate. Interest rate is decimal. N is the new one here, so this is the number of times per year. Underline that. The interest is compounded. And then the last one here would be T, which of course is time. And in this case, always years. So what's going on here is that you put your money into a bank account, and there's what's called simple interest at the end of the year. If you earned like 5% interest, if you put $100 in at the end of the year, you get your $100 back plus $5, that 5%. If you have something that's called compounded, maybe let's be like semi-annually. So after, so you put your $100 in after 6 months, semi-annually means twice a year. After 6 months, you would get half of your interest. So you get, if your interest is 5%, you get $2.50. And so now you'd have $102.50 in your bank account. And then over the next 6 months, that $102 would then earn the next half of your interest. But you earn the $2.50 from your $100, but you'd also earn the interest on your interest. And so with compounded interest, the more often it's compounded, the more times your interest is starting to earn interest, and then the more money you would end up making in your savings. So this is generally how most bank accounts work. Credit cards, like in loans and stuff like that, they all work on compounding interest. So when they tell you your APR, your annual percentage rate, you actually don't really use it because you have to look at how often the interest is compounded. So if something was compounded annually, that would be once per year. If something was compounded semi-annually, that would be twice per year. Quarterly would mean 4 times per year. Monthly would mean 12 times per year. You might see daily. Okay? If it said daily, that would be 365 times per year. So you need to make sure you take those words that are going to be in the problem and turn them into a number. So pretty much everything else will be, they'll tell you the principal, they'll tell you the rate, they'll tell you the time, but then they're going to give you a word, and you need to turn that into a number. So if $20,000 is invested in an account that pays, so what am I seeing here? There's my principal, investment, account that pays 3.5% annually, so that's my interest rate. I'll write that as a decimal though, that'd be R equals 0.035. Find the amount after 6 years, so there's T is 6. The investment is compounded quarterly. So there's our word for our N value, and quarterly means 4. So A equals our principal, 20,000 times 1 plus 0.035 over 4, all to the 6 times 4 power. So you just need to be careful how you type this in. with this, you can either do that math in your head, or as you type it in, make sure you put parentheses around that. So I'll go ahead and type it that second way. 20,000, 0.035 for 6 times 4. So plus 0.035 divided by 4, close those parentheses, to the 6 times 4 power. So kind of check on that left side, make sure it looks like it typed it out right. That 0.035 over the 4, and 6 and the 4 both being put up there in the exponent. $24,651.03, since that is money went around to the hundredth every single time. So 24,651.3. What amount would your grandmother need to deposit in order to be able to make a gift of 20,000 to you on your graduation from KU in 4 years? Best rate of return she could find is 3.75% compounded quarterly. So here we've got our rate, we have our in value, got our time. So what would she need to deposit? Means that this is the question. Our p value is our question, and she wants the end result to be 20,000. So now we know the answer. It's going to be 20,000. Don't know what p is. $4 years and 4 times per year. So 4. That's going to be a 16 up there. So we need to solve for p, which basically means what we're going to do is simplify all this stuff. So if you notice, we know all of that, so that means we can simplify all that down. So I'm going to put that part into my calculator. 1 plus 0.0375 divided by 4, all to the 16th power. Again, not really giving any idea about rounding here. We really should keep that number the way it is. I'm going to round it as I write it, but I'm not going to round it. I'm going to leave that number in my calculator. So it really does make a big difference with this stuff. Those little numbers. I think that was right. Yep. So next thing I'm going to do is go ahead and get rid of that 1.16. Again, I'm going to write it like this, but I'm going to go ahead and do it in my calculator the full way. And I'll show you what the difference is. So 20,000 divided by that. So I'm going to take 20,000, make sure I got enough zeros there. And then divided by, I'm just going to tap my screen. It'll bring that number down for me. Otherwise, you need to type that whole thing in there. And so I get $17,226.19. So that's what she would have needed to divide to input into the savings account in order to get that gift of 20,000 in the end. So let's look at it if we had rounded, see what kind of difference that makes. So it's about $15, looking at the difference, which may not seem like a bunch, but it is a difference. And so just showing how that rounding does make an impact. So try not to round too much when you're during the middle of a problem. That's why, if it was at the end of the problem, then rounding's a safer bet. But during the middle of the problem, not good. In certain situations, it matters more than others. But so 17,226.19. All right, last thing here, natural base E. So there's this number E, which is basically the amount of money if you put $1 in a bank account and then you had 100% growth rate. So think about like put a dollar in a bank account, and then after 1 year you get 100% back. So that means you get your dollar plus another dollar, so you get $2 back. Okay. So as we start to compound that more and more, so as this number of n goes to infinity, that number e starts to develop. That this actually doesn't get like bigger and bigger forever. Like doesn't grow off to like infinity. Doesn't mean you like get $1 billion after 1 year. I think that actually starts to level out. It has a limit. Okay. And it turns out to be about 2.73-ish. Okay. So I want to show you what that is. So e. So on this calculator, I have an e button over here on the right side. The e, the little e, and the capital E. So the little e is the one I want. The capital E is for like scientific notation. So on this calculator, I have to do like 1 times e to get it to come out. I know like on some of those TI calculators, if you hit like the E button to the _1, it'll tell you what the answer is. But I was wrong, 2.73, it's 2.72. So we see it's about 2.72-ish is what E is. So basically the most money you could ever get out of a bank account, the highest of interest would be, if you put in $1 and then you compound it an infinite number of times, you would get $2.72 back at the end of the year. That's what that's kind of going for. So, and then but a lot of bank accounts do use this number now, this number E. This is going to be important for other stuff that we do later, so don't forget about E. It's called the natural base. So we have a different formula for when E is there, because so we can't write down this. We can't make n infinity and plug that in. So there's actually a different formula for that. It's gonna keep looking. A equals P to the RT, so A pert. It's a pretty simple formula. You just need to know your principal and your rate and your time, and E takes care of itself. Where E is a number, it's not a variable. P, R, and T are variables. So and suppose you invest $12,000, so that's our investment. That means that's our principal. In a fund that yields 3.8% interest. There's our interest rate, compounded continuously. So make sure you see that word, continuously. How much will there be in 25 years? So we know P. We know R is 0.038, and T is 25. And 0.038 times 25 would go up here. So I just need to be really careful about how I type that in the calculator. We'll use parentheses around that. So 12,000 e to the 0.038 times 25. We'll not type that right. Parentheses around there. Until I hit that. So notice how the exponent does not have the 25 in it. So notice how big that number is too. Way too big. So $31,028.52. $31,028.52. That wrong. 30,028.52. All right, last problem. Suppose you have 3,000 to invest. It's our principal. Which investment yields a greater return over 10 years? There's our time. I got a rate of 6.5% compounded semi-annually. Or I've got 6% compounded continuously. It's got two different formulas. Okay. A equals P times 1 plus R to the N over NT for this guy. Compounded semi-annually, and then I've got A equals P times E to the RT for our compounded continuously. So make sure you're paying attention to that. amount, so we have 3,000 principal. 1 plus our rate was 6.5%, so 0.065. Over there, compounded semi-annually, which meant 2 times per year, times n to t, so that'd be 2 times t was 10. All right, so I'm going to type that in, 3,000, 0.065, 2 times 10. I got $5,687.51. 5687. Okay. Here I have A equals 3,000. E to the 0.066% times 10 years. 3,000 E, oops, caret 0.06 times 10. $5,466.36. 54663. 5466636. All right, so which one is higher? So obviously this one is higher. How much higher? So minus 5466636. 5, 1, 1, 2, 2. All right, well, there you go. So I'll wait to see what you guys need help with. Let me know.